For today, and it'll stretch in for the next couple days, is we're going to identify and we're going to graph something called a quadratic function. So take a moment real quick, and please just put a little itty bitty 2 above the quadratic. Because what does it mean to be quadratic? Notice that if I put an S in the front and erase the D, notice, oh my goodness, it's like square. And that's why we call that little 2 above, we call it a square. Why? Because if I had something here that was X inches long, and I converted this into a square just by pulling it out, and I'm talking about now the entire region inside, we call that X squared, the region inside. Generally, square helps us to deal with area. And so that's the basic concept. It's true that the word quad means 4, but really where does it come from? It comes from taking a one-dimensional object and making it two-dimensional. And in making it two-dimensional, you have to have 4 sides. So there is the etiology of it. And let's see here. This graph models a projectile. Project, to throw. Something starts here, comes up, and then what goes up must come down. The graph on the right models a projectile launched in the sky. If height is measured in feet, and time is in seconds, let's complete the analysis of this graph. Where does the projectile begin? And we say, well, at 0 seconds, this thing is at 50 feet up. So where does the projectile begin? It begins 50 feet up. Now, what does that mean? Is it on some sort of a stand? Are we on the top of a 5-story building? Are we on a cliff edge? Don't know. We just know it's 50 feet up for whatever reason. Now it gets launched. And after 1 second, this is where it is. After 2 seconds, this is where it is. Part 2. What is its maximum height? So as we see here, this is the maximum height. So we take it over to here, and clearly I'm off. So I would estimate it at 200 feet is the maximum height. Next, when does it reach the maximum height? At 3 seconds, which is this component, this axis, is 3 seconds. And the last question, when does it hit the ground? When being time. And we see where on the graph it hits the ground, approximately here. In class, what do you think that is?
6.75.
All right, so 6.7-ish is fine. If you said 6.8, you'd be okay. If you said 6.75, also okay. But 6.5, not quite. Let's review family of functions. So what do we remember about family of functions? All right, so it's a good thing we're having some review time here. The first thing we want to recollect is that this component here is called my parent function. My parent function. And parent function says, what's the basic graph look like? What's the basic characteristic of this function? So for example, this parent function over here, the absolute value, in its most simple form, is you put in any number and out pops the positive. So what's the nature of that graph? And you don't have to do this, but the nature of this graph is that everything's straight, but it bounces. That's it. We've got straight and bouncing. That's the nature of the absolute value function. So using the family of function rules, we can describe the graph without spending hours and hours with a table, without drawing all these crazy lines and making 100,000 points. All we say is, oh, it starts here, it begins here, it bounces here, etc. So remember, shifting. Shifting is also called translation. It's also called translation. And the shifting part is always dealing with the plus or minus. Anytime a number is being added or subtracted somewhere, we're causing a shift. We're causing a shift. So, just to recollect, inside adding or subtracting causes it to shift left or right. So H, you can think of H as the horizontal shift. H is the horizontal shift, left or right. This tells me this is the knob that moves the whole function left or right. K is my vertical shift. Just take the whole shape and move it up or down. That's it. Move it up or down. So over here, how do I interpret this? Well, this one right here tells me where I shift it left or right. I have to shift left 4. Why? Because I have to take the opposite of what I see. Always the opposite of the inside for the shift. Over here, that tells me to go down 7. In other words, my vertex is at -4, -7. So I just take the entire V shape, and instead of starting here at 0, 0, I'm going to start at -4, -7. So that's my initial place. That's where the bounce happens, the place of the bounce. Okay, reflection. The A in the front, A is positive or A is negative. If A is negative, that means we turn the thing upside down. We reflect vertically. We flip the thing upside down. If A is positive, there's no change. If A is negative, we take a reflection. So remember, over here, if A is positive, we're going to open upward like a V. But if A is negative, it opens downward like a rooftop. So now I know that my graph over here is going to go like this. I go bounce off that and come back down. Bounce, hit the ceiling, come back down. Or a rooftop situation. Now, I don't know how steep it is. I don't know if it comes straight up and bounces straight back down. I don't know if it's a slow going up and a slow going down. Or if it's just my normal setting. So that's the next part here. Remember that the last part is about compression and stretching. You could also say compression. So how do I refresh that? If the absolute value of A is between 0 and 1, in other words, 1/2, 3/4, something like that, it's a compression. It squashes it down. If the absolute value of A is greater than 1, then we have a stretch. It makes it tight. Makes it tight. So how do we interpret that over here? Well, notice that this 2 right here tells me instead of being at rest position like here, I have to make it tighter. Oh my God. Like so. Let's bring it back. So how do I graph this? It tells me there's my parent function, this nice little V that's in a resting position like that. This one turns upside down, starts way over here, and is tight. It's more tight. How much more tight? I go down 2, right 1. Down 2, right 1. And how do I know that? Because here it stretches by a factor of 2. Stretches by a factor of 2. Where does that 2 come from? It's just that 2 in the very, very front. The negative tells me it flips upside down, so it looks like a rooftop. The 2 tells me that it stretches out. So instead of going up 1, right, up 1, right 1, up 1, right 1, up 1, right 1 here, up 1, right 1, up 1. It goes down 2, right 1, down 2, right 1. All right, so let's do some defining. What's a parabola? A parabola is a U shape, and often just described as a U shape. It could be upside down as well, so that would be a parabola. It is not parable. A parable is a story that teaches a moral. So that would be
Maybe sideways.
parable. So that's a alongside reality. This is like alongside I forget what bola means. Okay. All right, quadratic function. What's the quadratic function? In other words, what's the parent function? The super parent function is just this. X squared. That's my parent function. However, generally speaking, it can be placed into this form. Sometimes it's called the general form. Learn to spell. Sometimes it's called the general form, and sometimes it's called standard form, depending on the context. And that form looks like this, where you have y equals ax squared plus bx plus c. All right, so these are parabolic shapes. These are parabolic shapes. And we have highs and lows. This one here and this one here. Both of these are each called a vertex, or vertices is the plural. However, in the given context, this one right here is called the minimum. This one's called the minimum. Why? Because it's the lowest point on this graph. If this were describing a satellite dish, this is the lowest point of the satellite dish, or a valley of some kind. What about this one over here? Well, this is a ball going up and coming back down. So this right here is the max, or also known as the maximum. It is where the ball reaches the maximum position. So each of those are called a vertex. And the vertex, by the way, vertex just means like where things change, where things change. And so the vertex would be the high or the low. The high or low of the parabola. All right, X-intercepts. I only want to point it out to you, not because you don't know what they already mean, but because they're extremely important when we're interpreting graphs. All right, so this here, these two, there's two of them in this context. This one, these are called my X-intercepts. Just by way of a preview, they're also called roots. They're also called solutions. And they're also called zeros. Also called zeros. All right, and the last thing is called vertex form. Hopefully this looks familiar. Why? Because look, it looks almost exactly like this right here. It has your H, your K, and your A. Except instead of having straight bars for absolute value, we have, the key thing about the quadratic is we have a square. The moment I see square, I know that this is my basic shape. My parent function looks like that. So, the vertex form here. This tells me a bunch of stuff. Number one, it tells me that my parent function is y equals x squared. What else does it tell me? Well, remember what A does. A tells me A is positive, A is negative. That means A is positive, means it opens up. A is negative is a sad face. Oh, it's so sad. Opens downward like a smiley, unsmiley face. All right, what about H and K? Remember H and K tell me about shifting. H and K tell me about shifting, and more specifically, it's the vertex. Remember, the H is the opposite of what I see. I see a minus H, so I keep the positive H. The K is exactly what I see, and that's my vertex. In other words, what's the highest or the lowest point the ball goes? That's what the vertex tells me. And lastly, A also tells me, does it go wider or does it go tighter? Am I going to have a very open thing like a satellite dish? Or am I going to have a very tight situation like a ball coming up and down very close nearby? And let's apply our stretches. Let's apply our stretches here. We're going to graph each function and see how is it a stretch of the parent function. So let's see here. What's the stretch? How does it stretch it? Well, number one, the negative tells me that it opens down. The negative tells me that it opens down. And the 1/2 tells me that it compresses. In other words, it's going to make it more open like this. Before we even get into more of this, though, we do need to understand, why is this the parent function? Why is this the parent function? So we're just going to do a really quick table of values. When you plug in a 0, 0 squared gives you 0. And that's this point right there. When you plug in a 1, class, what is 1 squared? 1. It's 1. So look. 1, 1. Odd. This is where things start to change. When you plug in a 2, what do you get? 4. Oh, a 4. So look how it jumps up. The 2 jumps all the way up to 4. So does the negative. And if I do 3, it jumps up to a 9, which is way up high. So when we say it's exponential growth, oftentimes people mean something like this. That it's not just going in a straight little line like this, la, 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 but it's like, whoa, growth. Whoa, rabbits all over the place. Dag. Where'd that mold come from? Grows all over the place. Not a very slow thing, but just zoom, like that. What does this mean? This means now I'm going to flip this thing upside down, but instead of going from to this point, the 1, I'm going to go down, and I'm going to be at the half. Why? Because it says cut everything in half. Notice with this one, at -1, it goes to 4. So instead of going to -4, flipping it upside down, I cut that in half, go to the -2. This one here goes to 2. And the same thing. So notice that this is going to be a more open situation.
But why do you make them, like, why do you make 2 of them? Like, why does it reflect?